Hello, everyone, and welcome to quantum mechanics, electronic structure, and periodic properties. Uh, this is going to be a very, very long chapter that we're going to get through lots and lots of videos. We will get through it together. And we're going to start off here by kind of talking about a little bit of a humorous example that is often used to consider the craziness that is quantum mechanics. You've probably heard of Schrodinger's cat before. Um, it is a decently well-known thought experiment, even outside of the scientific community. There's actually a whole episode of the popular TV show Big Bang Theory where throughout the episode they keep referencing the Schrodinger's cat thought experiment. And essentially what the thought experiment is meant to do is it's meant to show that quantum mechanical principles do not work at the macro-sized level. They are crazy at the macro-sized level because what the premise of the experiment is that you are going to make an assumption that the way things work at the atomic level, at the quantum mechanical level, that things in the macro level work the same way. So if we make that assumption, if we make the assumption that the stuff that happens to atoms, the same type of things happen to cats, then this is what will end up happening here. So we have this thought experiment where we have a box, and inside the box we have a radioactive isotope that could decay at any second. So we don't know if it's going to happen in 1 second, in 100 seconds, in a million seconds. Like, we don't know. We have no control over it. It could happen at any time. And when it does decay, the decay of that radioactive isotope is detected by this thing over here. And when it detects it and it says, something happened, this thing decayed, it's going to release a hammer. In this case, it doesn't have to be a hammer, but just going to release something that is going to break a jar of poison and release it into the box. So essentially, some random occurrence, the decay of the radioactive isotope that we have no control over, will release poison, killing anything that's in the box. So into that box we put a cat, because apparently we are not cat people. So we put a cat into that box, and we then close the box. And in closing the box, we can no longer see what is happening in the box. Now, according to quantum mechanics, if cats and jars of poison and everything like that behaved in the same way as electrons and atoms behaved according to quantum mechanics, the moment that we closed that box and could no longer see that the cat was in there and alive, the cat became a superposition of cats. Essentially, the cat became both dead and alive. The moment we could no longer see what was happening, because at that very moment there was a chance that the radioactive isotope decayed and released the poison, killing the cat. Because there was a chance that it could happen, it did happen. Because that is essentially what quantum mechanics says. Quantum mechanics is not what is happening. Quantum mechanics is what is the probability of this happening. And electrons and tiny things like that really behave on that basis. Electrons don't always behave as particles, as we'll talk about later. Instead, they behave like a wave of probabilities. There's a chance that the electron is here, but there's also a chance that the electron is here, and 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 here. And so because there's all these different places where the electron could be, it is in all those places. And so the Schrodinger's cat experiment is telling us that if things on the macro-sized level behaved in the same way, we would have madness like this going on, where we have a cat that is both dead and alive, because there is a probability that it is both dead and alive. Things on the macro scale do not actually occur solely based on probabilities. So that is the point of the Schrodinger's cat experiment, that we cannot take the stuff we're going to do with quantum mechanics and apply it to cats, or even to, fleas. In anything that we can see for sure. We cannot apply quantum mechanics to it. Quantum mechanics only really works. It only has a significant effect on the way things behave, I should say, when you get down to extraordinarily tiny things like atoms and electrons. Things that are larger, quantum mechanics is still there. Quantum mechanics is still determining what happens, but the probabilities kind of get washed out when you get to really large things, and they don't have as much of an effect. Technically speaking, you really don't have to get much larger than even an atom before the weirdness of quantum mechanics kind of gets washed out. It really is just atoms and smaller are the only things where we have to take quantum mechanics into account. Of course, the one thing that Schrodinger did not account for is the fact that cats, while they do like being in boxes, they do not like being trapped in them. They will go into the box willingly, but if you try to keep it in there, it's going to get angry. Alright, before we can talk more about quantum mechanics, let's talk about light. Because light is going to be kind of our segue into quantum mechanics. If we can understand what's happening with light, we can better understand what's happening with electrons, and the electrons will really give us our foot in the door of quantum mechanics. So we're going to have a kind of a multi-step process here to get to quantum mechanics, starting with light. So that begs the question then, what exactly is light? Light is actually something that I was interested in at a very young age, actually. It's one of the very first things that actually piqued my scientific interest was, what is this stuff that we use to see? Like, it's kind of something we take for granted at this point, but we really shouldn't. It really is a fascinating topic, light. And truthfully, we don't even completely understand light. We understand a whole lot about it, don't get me wrong. We understand it very well, but we don't 100% understand what light is, and how it works and how it operates. But for our purposes right now, we are going to settle with knowing that light is electromagnetic radiation, or EM radiation as it's sometimes called. Light is a wave. It is a wave of energy that propagates through space, space being just volume, not necessarily outer space, although it does travel through outer space as well. And it moves at a constant speed if it's in if it stays in the same medium. And what I mean by that is that light actually does travel different speeds if it's moving through different material. This is not something that's commonly known, but in a vacuum, light travels at this speed, 3 times 10 to the 8 meters per second. And that is the maximum speed of anything in the universe. Nothing can move faster than that. And we know that is true because if it were physically possible for anything to move faster than 3 times 10 to the 8 meters per second, light would go that speed. Just physically speaking, the way the physics works out, light doesn't go at 3 times 10 to the 8 meters per second because that's just the speed that light travels at. Light travels at this speed because it is the fastest possible speed. And so if it was possible to go faster, then light would go faster. Light isn't limited to this speed just because it's like, this is as fast as I want to go. And it's just the actual physical constraints of the universe keep anything from going faster than this. But if it was possible to go faster, then light would. There's been a few situations over the years where excuse me, different groups of scientists have done experiments and thought that they've found things going faster than 3 times 10 to the 8 meters per second. And in every one of those cases, it's either been found that they made a mistake, or it's been found that no one was able to reproduce what they did, so they could do it once, and then they could never reproduce it, which is pretty much the same as saying they made a mistake. They might not know what the mistake they made was, but if you can only do a thing once and you can never do it again, then scientifically speaking, something went wrong. So, in vacuum, light travels at this speed, but light does actually move slower than this through air. Not a whole lot slower. It's still incredibly fast. I forget exactly what the speed is, but it might lose like maybe, I don't know, 1% of its velocity when it's traveling through air. In general, if it's traveling through denser materials, it tends to go slower, I believe is the way that works out. But for our purposes, we don't actually care. We're just going to assume that it is always going to travel this speed. So light is always going to move 3 times 10 to the 8 meters per second, just to make it simpler for us. So we don't have to worry about, okay, is the light traveling through air? Is it traveling through water? Is it traveling through vacuum? We're just going to assume that the speed is always 3 times 10 to the 8 meters per second. All right. So a few other things here about waves, just in general. A wave is a disturbance or oscillation that travels through space-time occupied by a transfer of energy. So all waves have energy. Some waves have more energy than others, but we can take waves and also break those down into even smaller groups here. So separate waves into mechanical and electromagnetic waves. So mechanical waves we are very familiar with. These are waves that need something to travel through. So they actually have to have a medium to travel through. So sound waves, ocean waves, for example, these have to have something to travel through. Sound waves travel through air. So they're actually oscillations, they're waves of energy that get transferred through the air. And so you can hear the sound of my voice because there are waves of energy being shot through the air of your being produced by your speakers or by your earbuds or whatever it is that you're using, and those waves of energy are impacting your eardrums, and your eardrums can feel the vibration of those waves of energy. So things like ocean waves and sound waves need something to travel through. There's the famous, no one can hear you scream in space. It's because there's no medium for sound to travel through in space. Electromagnetic waves, on the other hand, do not require a medium. They can travel through vacuum. They can move through a medium as well, which is very, very good. Otherwise, we wouldn't be able to see anything because we live in a medium. We live in the atmosphere. Excuse me. It's not coronavirus. So they can travel through a medium, but they don't have to. They could travel through vacuum. Few other quick things about waves here before we call it for this video. Every wave has a wavelength, and every wave has a frequency. The wavelength is just the distance from one point on a wave to the same point on the next iteration of the wave. So the wave is just kind of moving along like this. Sorry for my poor wave drawing. But it's just moving along. You can see how it reaches a point every, and I was trying to draw those to be where they would be about the same distance, and I didn't quite do it right. But here at the beginning, they're pretty close. So this distance from one point on the wave to the next point, when the wave to the same point in the wave the next time it comes around, that is the wavelength. And that will be different for every different wave that you come across. They can be shorter or longer. Sometimes they can be extremely long. Things like radio waves, especially very long radio waves, they can have meters long wavelengths, or even thousands of meters long wavelengths. Or you can have other waves like sound waves, where the wavelength, depending on the frequency, it could be just maybe a couple centimeters or even shorter. It just kind of depends on how high pitch the sound is. So the wavelength is that distance from one point on the wave to the same point the next time the wave comes around. And you can see here it's the same distance. You don't have to pick the peaks. You could pick the crests as well. And this would be the same distance here as it is up there, or here and here. That's the same distance. And by the way, don't do this and this. That's actually half of a wavelength right there, because we want it at the same point, which means that here the wave is going down, here the wave is going up. So even though it is crossing the same point here, it's not the same point in the wave, because the wave is going in different directions. So when it goes back down again, that would be one wavelength. So every wave has a wavelength. Every wave also has a frequency, and the frequency is how many times the wave goes through its wavelength per second. So how many cycles it goes through per second. So again, the cycle is how many times it goes through that wavelength. And for something like light, let me see, do I talk about this here? No. So for something like light, where the wavelength and the frequency are directly tied to one another, and really most waves are the same way, but they're not all going to be exactly the same as light. But with light, the shorter the wavelength, the higher the frequency. And the reason for this is that light, because it travels at a constant speed, this speed, because it's always traveling at 3 times 10 to the 8 meters per second, and because the wavelength can change, if it's traveling, for example, this distance, and I know this is kind of a ridiculously small distance, but let's say that light travels this distance in 1 second. And it has to, because again, its speed is locked. The speed of light is not going to change. So it's always going to travel this distance in 1 second. Well, if the wavelength of this light is, is ridiculously long, so that it only goes through one wavelength as it goes through this distance, then it's only going to go through one cycle per second. So that would be a relatively low frequency. If, on the other hand, the wavelength was not really long, if instead the wavelength was really short, so that it was something like this. Yeah, sorry. My waves got really messy there towards the end. But if we had this wavelength instead, the light still has to travel this whole distance in 1 second. I know when I was drawing it, I went slower just because, I am a limited person. I can't draw it that quickly. But the light is going to travel that distance in the same period of time, in 1 second. And it's not going to go through just one of its cycles. It's going to go through 1, 2, 3, 4, 5, 6, 7, 8, 9 cycles in that second. And so the frequency is higher with lower or smaller wavelengths. So the wavelength and the frequency are actually inversely proportional. As the wavelength goes down, the frequency goes up, and it must, because again, the speed of the light is constant. And so if the light is traveling the same distance in a second, but you can fit a whole lot more wavelengths into that distance, then the frequency has to be higher. All right, I think we'll pick up here with this slide in the next video. I will see you then, and we will start talking about the different kinds of electromagnetic radiation and comparing one versus another, and then also doing some conversions between wavelength and frequency for different types of light.